Okay, Assalamualaikum and good day. So we will continue our lesson on BJT biasing. Okay, so what is BJT biasing? Okay, alright. So biasing, okay, is used, if you look in the slide, it means that we want to put proper DC voltages and currents at a transistor terminals, collector, base, emitter, so that the device is in the required operating region. Okay, since in our, remember in our lesson here in this course, we are going to analyze and design amplifier. So we want the BJT to be in the amplifier region. Remember that last lesson I said in which region that this BJT works as an amplifier? Okay, the answer is forward active. Okay, forward active. So meaning that in this area. Okay, if you want to fix, if you want to bias it here, okay, so we want to have a proper IC current, and we want to have a proper design IB current, and we must have a designed VCE voltages. Okay, so that it will be in our desired region. So that now, if it is in this region, then we will have the BJT to work as an amplifier. Alright. Okay. Okay, you can read these slides. Okay. Okay, this also you can read. So basically we have BJT has 3 terminal, base, collector, emitter. So we will control, usually one of the terminals will be connected to the ground, and we need only to control the voltages and current on the 2 terminals. So how to control the voltage and current on the other 2 terminals? Okay, when we put a certain voltage and current at the terminals of BCE here, then we can force the BJT to be in the desired region. Remember that in this diode, okay, we want the diode, okay, for forward active region, the base emitter junction must be forward bias and base collector junction must be reverse bias. What does it mean by forward bias and reverse bias? Okay, if it's a forward bias, base voltage will be higher than the base voltage will be higher than the emitter, right? Because this is PN junction. Okay, the current flow through here, so base must be higher than emitter. So then it will have, so we have to put a proper voltages here. This must be higher than this one. Okay, now what does it mean by base collector junction reverse bias? Okay, if it is reverse bias, now, okay, supposedly it is forward here. So now the current, the diode is reverse bias, meaning that the voltage at the collector is higher than the base. So that is why it is reverse bias here. So in order for us to make this BJT to be in this forward active region, okay, BJT, let me try to put this camera, BJT in forward active region. Okay, so if we have this way, this is our collector, base and emitter. This way is forward bias. Okay, forward bias. This is reverse bias. So that supposedly it is this way. So it is this way, right? So this VC reverse bias. So VC is higher than VB. Okay. Therefore, for this one, VC must be greater than VB and VB must be greater than VE. Then we will have this BJT to work is in the forward active region. Okay, let's look at the slides again. Where's the next one? Okay, these are the typical biasing, DC biasings for BJT. The first one, the simplest one is, let me just put this properly. Okay, right. Okay, or okay, never mind, this this way. Okay. The simplest is the DC bias configuration. Okay. Okay. The simplest is this is the fixed bias, meaning that we put a resistor here. Okay. We put this resistor so that, okay, and also the resistor here, so that okay, we can design so that VC is higher than VB and VB is greater than VE. In this case, VE is ground, 0 lah. Okay. The second, before that, the second configurations is the emitter bias. We have this RB here, which is the fixed bias, but we include RE. The reason we put the RE here, the resistance at the emitter junctions here, is to improve stability, and additions of emitter resistance makes DC bias currents and voltages remain closer to set values even with variations in transistor beta and temperature. Okay, if you do the analysis of this circuit, we can see that the current flowing, okay, the current flowing, the DC current and voltages will not, if beta is changing, it won't have any much of variation. Okay. Please try to understand this one. This is to improve stability. What does it mean? Stability, stable, right? Straight, like stable. Okay. So so it is not very like up and down, right? That's what it means. Okay. Later we will look into that. Okay. Then the last one, I think the last one. Oh no. The next one is the voltage divider biasing, where we have this resistor 1 and resistor 2. Instead of only one resistor, we have 2 resistors now. This is called voltage divider biasing. And this one, ICQ and VCQ are almost independent of beta. Okay, so it's not depending of beta of the transistor. What is beta? Beta is the transistor current gain. It's a this is the transistor parameters. Okay, when people go to develop, to fabricate these transistors, and then they measure and they get the beta value. Okay, the last one, the last one is collector feedback bias, where we have another resistor bias between collector and base, this R2 here. This is also, by having this, is also to improve stability. This is actually a feedback type. Okay, feedback type. Okay, can you see? Okay. Oops. Okay. I want to minimize a bit so that. Okay. Can you see here? There is no AC current source, only DC current source. What is the DC current source? Sorry, DC voltage source. And okay, there is no any AC source. We only have DC source, which is VCC. Okay, for biasing, what we only need to put the DC source only. Okay, same thing here, only DC source. Okay, for this one, it's not included here. Okay, by having DC source here, okay, there's no AC. Suppose there's no when we are doing the biasing, we don't need the AC signal. This is when this is the complete circuit lah, complete amplifier circuit. Okay. We only need the DC source. Okay. Alright. Okay. Okay, now let's analyze this circuit here. Okay. Alright. Okay, this is the fixed biasing. Okay, when we are designing, okay, an amplifier, the designer set the biasing where we want it to be biased. In this example, okay, maybe I can increase a bit now. Zoom a bit. Okay. Alright. Okay, so now for this one, we design that our operating point, they use the term Q point here as, okay, V out equals to 6 volts. Okay, meaning that V out equals 6, V out is also equals to VCE because E is grounded, so V out is equal to VCE. If you don't understand why V out equals to VCE, please come to see me. Okay, and then we also design so that IC equals to 20 milliamps. Why? Okay, when VC equals to 6, IC equals to 20 milliamps, it will the biasing point is here. In which region now for BJT? It is in the forward active region, in this area. It's not down here or it's not here. This is saturation region. This is cutoff region. So because we wanted the transistor to act as an amplifier, okay, so we want to be in this region. You can design here, you can design here, you can design here, as long as it's in this region. But there are pro and cons lah by choosing the biasing point. That one later lah. If you go to study further for your masters, then I'm not so sure. Maybe there are some other courses lah that explain to you to choose certain biasing point here. There are pro and cons lah. Okay, alright. But for us, we want to be, let's say we want to design a linear amplifier. Okay, linear means linear. Never mind lah, linear amplifier. It is in the middle here. Okay, alright. So this is what we design. 6 volt and IC equals to milliamps. Okay, this one is known. Okay, when we buy the transistor, it comes with a data sheet. In the data sheet, it has the beta values. Okay, beta values also can vary. Sometimes they have min and max. Some of my courses before, I explain lah. I show you the data sheet. Okay, so beta value, sometimes they call beta. For power electronics, it's called HFE. Okay, alright. So this is beta value. What is this? This is small signal current gain. Okay, because we are studying microelectronics, so we are dealing with small signal. Okay, that's why this subject is called microelectronics circuit analysis and design, because micro means small. Okay, so we are dealing with small signals. Okay, milliamps, volts only, not amps. Okay, alright. So beta value is 100. So the typical value for micro small signal BJT is also high. For power electronics, power BJT, the beta value usually low. Okay, alright, never mind. Okay, now this is known from the data sheet. This is what we design. Okay, now if we also choose our VCC. Our VCC equals to 10 volts now. Okay, and then this is VCC, right? The supply voltage coming from the supply voltage there is 10 volts. Okay, so now if we want to get a 4 volt drop across the collector resistor, so this is 10, this is 6, so it means 4 voltage drop. Okay, 4 voltage drop across the collector resistor. Okay, we put a resistor here. At 20 milliamps, require a resistor value. Okay, now with IC equals to 20 milliamps, so by using, what is this? How do you get this equation? By using Kirchhoff's voltage law. You know how to do this? I hope you do, 10 minus 6 over current flowing here. I hope you know how to do this. Later, if you are not sure, come to see me. So you get 200 ohm. So this is the design value. Okay, 200 ohm here. Alright. Alright, now we want to put the RB value. Okay, this is our design base resistor value. Okay, to find the RB, find the base resistance that will give this current. Okay, KVL. So we apply. We want to have this, right? Okay, what is VB? Okay, VB is your, because this is connected to, if you look at the here, RB is connected between base to VCC. So that's why they just put this VCC to down here. Okay, you can just put it remain. Okay, you can still apply the equations here. Okay, so this RB, okay, apply a Kirchhoff's voltage law across this loop. It's VB equal minus RB minus 0.7 equals 0. This is one loop. So you rearrange this equation and you get RB equals to VB minus 0.7 over IB. Therefore, RB equals to 47 kilo ohms. So this one, which is in the yellow box here, this is our design value. Okay, this is our design value. Okay, so this is the complete circuit now. See, this is ready. The transistor, when we put the voltage supply here with these two resistors, this transistor is ready to amplify signal. Okay, but there's no input signals yet. This is only biasing. I hope you understand. Okay, this is just ready. Okay, when you do this biasing, you can, without any AC signals, this is already ready. We just want to bias the transistor to become in the forward active region. I hope you understand this equation, okay? Alright. Okay, next. Okay, this is another topology. Okay, this is emitter bias DC biasing. Okay. Okay, so this is the analysis. Okay, like FET, BJT parameter can vary from device. Okay, this is the reason where we want to have this RE, the emitter resistor at the emitter base here. Okay, because of the variation. Okay, you can read this one. And then maybe I can just read. Okay, like FETs, the BJT device parameters can vary from the device to device. Another concern is the positive temperature coefficients of beta. When current is passed through a device, its temperature, okay, the transistor temperature will increase. Of course, it has some heat, right? So it has some, the temperature will increase. In a BJT, a temperature rise increases the current gain, allowing more current to flow. Seriously. You will, if you don't properly manage your temperature, the current flow, and sometimes it can short it, okay, short and burn it's not properly handled, can burn the BJT, okay. Okay, this in turn makes the temperature go up further. In some cases, this process may continue until the device is destroyed. See? This is called thermal runaway. Okay, a term called thermal runaway. Okay, so adding a resistor in the emitter adds negative feedback to stabilize the bias point. In the same way that adding a source resistance helps the FET bias circuit. Never mind. This is the we will look into the FET MOSFET in the chapter 2. Okay, so the difference between this and the previous one is at this junction. Okay, now you have. You just have to analyze, you have to find the RB and RE value, right? Okay, now, we have two unknowns. Okay, if you want to solve this, we want to design the RB and RE value. There are two unknowns, okay? So therefore, we have to get two equations, right? So first, we have to get this equation first, the loop. Okay, this is just to find the RB and RE, eh? Okay, now, okay. Oh, okay, wait. Oh, okay, wait. Okay, here. Okay, wait. Okay. Alright. Here, you find the Kirchhoff's voltage law across this equation. So, VB minus IBRB minus 0.7 minus IERE, because our current flowing through this resistor is IE, emitter current from E here. Okay, you must know that the relation between IE and IB. Okay, this is the transistor. Okay, IE equals to IB plus IC, because IC equals to beta IB, so that's why we have this equation. Okay, I hope you know how to get this equation. If you're not sure to get this equation, please let me know. I will see you in class again, and then please raise up if you are not sure how to get this. Please don't be shy. Okay, alright, or any equations here. Okay, so rearrange this equation. You get IB equals to VB minus 0.7 over RB plus beta plus 1 RE. Okay, alright. What is this RE beta plus 1? Okay. Okay. So now we name RB equals to this equation, okay? Alright, so now since IC equals to beta IB, okay? Let me just see what is, okay? So we put beta and put everything in this equation down here. Okay, it's mentioned here for large beta, the collector current approach a value that is independent of current gain. Okay, if beta is very, very, very high, see beta over beta, so it's almost cancelled off. So, equals to 1. So, not much difference. So, it's independent. Okay? So, IC becomes VB minus 0.7 over RE as beta is infinite. So beta cross with this beta. Okay. Alright. So IE is almost similar to IC. Okay. And what is VE? VE, VB minus 0.7. Hold on. What is this? VE. Okay, because I think this is will give you around this equation, so that because the current IB will be very small. Okay, all right, so that's why VB minus 0.7 is not equal. Okay, but you solve this equation. Okay, all right, so this is what it means. It will be independent of current gain, so that not much of variations here. Okay, we will find an example later in our class, and then we will do this equation. Okay. Alright. Let me see what else being discussed. Okay, this is another important topology. This is the voltage divider biasing. Okay. For voltage divider biasing, we have this R. Okay. So we have to apply a circuit technique. Okay, to solve this problem, to find the resistance value. Okay, all right. So we have to apply Thevenin equivalent circuit. You have learned Thevenin equivalent circuit in previous classes, electronics 1 or circuit theory. So it is being applying here. So you cut this circuit here. All right. So this RB and RB2 becomes RTH, and this is parallel. RB1 and RB2 is in parallel, and we find the Thevenin voltage by this at this point. So it's RB2 over RB1 plus RB2. Please don't put RB1 on top, because I've seen people make mistake by finding the Thevenin voltage by putting the RB1 here. Okay. Okay. Alright. So now after you already convert the circuit to Thevenin equivalent circuit, then you can solve the same way you solve the biasing, like the fixed bias circuit previously discussed. Okay, so you with one voltage, one resistor, but now it's not VCC. VTH is different voltage. Okay, this is the voltage, but the way you apply to find RTH here is same. Okay, and then you can just say choose one value to get this RTH value. Okay, let me see what else. Okay, so this is another way. Okay, maybe you can try to solve, okay, with this value here, 5 volts, 330 of this resistor, R1, 3.33 kilo ohms for R2. With this transistor, just choose beta equals to 100 for this transistor. I want you to try to apply, to find out what's the voltage here, what is the voltage here, what is the current. Okay, because it's already give you the design values. When you have a design values, it means that you have to analyze it. Analyze where is the operating points, whether it's in the, whether it's, if now with this value, whether this transistor is in the forward active region or not. Okay, all right. Okay, so this is the end of our, I want you to try this and let me know whether this transistor is in the forward active region or not. Give your reason. I'll see you in class then. Okay, see you, bye. Assalamualaikum.